Okay, so I hope that last video wasn't too terrible and you slowly start to figure it out. Okay, I know this isn't ideal, but it's what we've got. So let's keep going with those steps in the back of our head. There's no real tricks yet. It's just what looks the most complicated in this question. So I've got two functions here. I've got cos of 3x times the cube root of sine of 3x. Now the dx is just attached to whatever function you're not substituting out of, okay? So I'm looking at this one, and I hope it's fairly obvious that the cube root part, whatever function you're doing, is more complicated. I'll start with that being my let statement. So let u equal whatever I'm cube rooting, okay? Now, if this doesn't work, that's fine. We just erase it and we try it a different way. And eventually it'll work. So I've got my let statement, so I'm going to take the derivative of both sides. The derivative of sine x is cos 3x times 3 dx. Okay, I look here and I see the cos 3x dx, so I'm gonna circle that for you. Cos 3x dx, like so. I see that in my question as well. Cos 3x dx, perfect. So I'm going to isolate that by dividing the 3 out. So that cancels. So now when I go back over here and substitute all my u stuff back in here, I'm going to take the 1/3 out, as I've been doing consistently. And I've got the cube root of sine 3x. So I'm going to replace that with the u, and I'm just going to automatically put it into exponential notation, du. So I've got u to the 1/3 du. Apply the antiderivative now. So 1/3 u to the 4/3, and of course divide by 4/3 is timesing by 3/4. And now I can substitute everything back in. We get 3/12. Well, 3/12 reduces to 1/4, I guess. So maybe I won't put 3/12. So I'll just say 1/4 because this cancels with this one. And then our u is sine 3x to the 4/3. And if you put that into radical notation, that is 100% fine. So there's your answer. Like so. Okay. Hit pause, finish those notes, and go on to the next example. Here we go. E to the x over e to the x plus 1. Again, try to look at it and say what function looks most complicated. I think the e to the x plus 1, so that's where I'm starting. And again, there's no rules. That's just the way I think about it. So I'm going to let u equal e to the x plus 1. And if I take the derivative of this and it's not the same, either I messed up my derivative or I got to flip it around and do something different. So when I do this now, I get the derivative of u equals the derivative of e to the x is just e to the x, derivative of 1 is 0, dx. So again, I notice there's my other function and it matches exactly the way it is in the question. So when I go back and substitute everything in, I get du over u. So I can take the integral of that. So the integral of 1 over u is the ln absolute value of u. Put my u back in. That's the ln absolute value of e to the x plus 1 plus a constant. I can double check if I want by doing the derivative just to see. I'm pretty confident that that's what it is. Moving on. Okay, here's something. I never mentioned this before. The integral symbol there, that's all that squiggly line is just doing the antiderivative or the integral. And integral is kind of doing the area under a curve is what it is. This is a definite integral. So this is kind of saying from x is 3 to 0. So I'll just do something goofy here just for fun. So there's some graph looks like this, for instance, and let's say this is 3 and this is 0. What this question would do is give us the area under the curve. if we actually applied it. Now, I'm not going to spend too much time on this. This would be this is the next unit. But I'm going to show you how these definite integrals work because it's really, really easy. Okay? So I'm going to erase that graph Okay, so the graph's gone here. So now you don't do anything different with this. Now there's kind of two methods you can do with this. You can apply the 3 and the 0 into your u statement as well, or you can substitute back your u statement in and then just do the definite integral at the end. But I'll show you all that. So of course my u statement is the more complicated part. I should have my dx in here. Whoops. Dx I should have wrote right there. Okay, so my u equals 2x minus 3. I take the derivative of both sides. I get 2 dx. There's no 2 in there, so I got to isolate the dx. There it is. So when I go back into this, I'm going to go and substitute the integral of 1 over u. Take the 1/2 out, and that's du. Now, what I'm meaning by this whole u thing is, you can see here that x is 0 and x is 3. So when x is equal to 0, u equals -3. Okay, by just substituting 0 into there, I get u is -3. And when x is 3, I get u equal to, well, 2 times 3 is 6, minus 3 is 3. So now when I would substitute this in, I'm going to put this in yellow. Because I'm using the u statement, I would have to say where 0 is -3. And my x is 3, u is 3. So it didn't change much there. But I have to change those as well. Now, I don't have to use those in the end. I can, once I go back to the x, that's fine. Either way, we'll come back to that. When I go and do the derivative of this now, I get, or the antiderivative of this, I get 1/2 ln of u, and I move those numbers over to here, so -3 to 3, like so. And now I can go and just solve this as it is, because it's not about what is the integral, it's actually asking for a solution. So I'm just going to plug this in right now as it is. So let's go like this. How you do this is you subtract. So we say 1/2 times the ln of, we start at the top, so the ln of 3, subtract the ln absolute value of -3, like so. So all I did was I substituted this value in, the 3, and then I substituted the -3 in, and I subtract that. Now I could have put the half in and just had it all in there, but it all works out the same. So as we can see, the ln of 3 minus the ln of absolute value, -3 is ln of 3, so that's 0, so it's 1/2 times 0. So our solution here is 0. Okay, and if you actually graph this, you would understand that the area under the curve is 0, because there'd be nothing. It would eliminate itself. Okay, so there's how you would do a definite integral. Now you don't have to overthink that too much. I'll do another one where maybe we substitute the x back in and do it that way. Okay, so here's a perfect example. So I'm going to go and do this with substitution because I can't do the power rule the way it is. So I'm going to say u equals 5 minus x. 5 minus x. Take the derivative. I get -dx. Now, when x is equal to 1, I like to put it right here, u equals, well, I plug in a 1, I get 5 minus 1 is 4. And when x is equal to 4, I get u is equal to 1. All right, so now I have to still isolate my dx because there's not a negative dx here, so I'm going to divide by a -1, which is not all that crazy. So we'll just factor out a negative, factor out a -1 out of the whole thing here. And we've got the integral of 4 to 1. These are our u values now. Now, there's always some discussion on whether you have your 4 on the top, 1 on the bottom. We're just going to leave it like this for now. And then we've got our 5 minus x, which is u to the 1/2. Because I said it's not going to matter because we're going to substitute back in anyways. Du. So I'm going to go and do the integral of this. So the integral of this is going to look like this. U to the 3/2 times 2/3. 1/4. Okay. But before we actually plug in, I'm going to switch it back now into terms of x. So it doesn't matter. So it's going to be -1. 5 minus x to the 3/2 times 2/3. And now I'm going to put the x values back where they belong. So 1 and 4, because we're now talking about x. So here we go. Let's take this whole thing, -1, and let's try and simplify this. I'm just going to stop it here and just put the numbers in and do the mental math so it's not to waste your time to listen. Okay, so there it is. So all I did to get the 2/3 is I put the 4 into x. 5 minus 4 is 1, so 1 times 2/3 is 2/3. And then I put the 1 into the x. I got square root of 4 is 2, cubed is 8, times 2 is 16/3. So now, there it is. So 2/3 minus 16/3 again. Distribute the negative, and I get -2/3 plus 16/3. So your final, not fourths, 16/3. So when we simplify this, we get 14/3. There's the area that would be under the curve of this graph. And we know that graph would be in horizontal reflection and all that stuff, but we're not too worried about that right now. Okay? So that's how you do a definite integral. Here's a little bit different one. This one here, when I look at the bottom, I clearly see that the function on the bottom is the more complicated one. But when I do the derivative of that, I get 2x plus 8, factor that out. I'm going to be left with an x plus 4, and I'm just doing some mental math in my head thinking about this. Well, I don't have an x plus 4 in that function up top, so there's got to be something else I can do. Now, again, looking forward, there's partial fractions that we could apply to this stuff, but I don't want to even think about that. I just want to show you another way to try to look at this. And I noticed that this down here is a trinomial that can factor pretty nicely. So what I'm going to do is I'm going to take that over here and say x squared plus 8x plus 4. And when I factor that out, I get x plus 4 squared. Again, doesn't mean much, but it's just a way of simplifying something. Because I've taken that, quadratic, and I've made a linear function out of it. And linear functions are really nice and easy to deal with. I haven't changed the question, I've just changed the way it looks. So now, if I let u equal the inside of that exponent, the derivative of x is just 1, so it's gone. So that's just a little trick to help you use substitution. Sometimes simplifying a polynomial will help you. So if I do the derivative of u, I get dx here now. So now the integral, I get 1 over u squared du. Of course, go do the integral of this, and it's going to be negative u to the -1. Whoops. And then substitute my value back in, negative 1 over x plus 4 plus the constant. Whoops. Plus the constant. So there is a different trick. You don't see it a whole bunch, but it appears every once in a while, okay? Where But once you do partial fractions, I don't know which way I would do this one automatically. I think I would still use substitution, but eventually some of you will use partial fractions almost all the time if it's possible.